Hi everybody, I wanted to give you a little bit more information on this centripetal force activity. So basically here's the setup. This is the moving mass. I called it M sub M for moving mass. And here's the washers. And the moving mass is going in a circle. And let's take a look at this in a little more detail. So for this one I've called the normal force, moving mass times g, and it's going in a circle. There has to be some force towards the center of the circle, and it's the tension that's towards the center of the circle that allows the moving mass to go in a circle. Now I've called it F sub t for tension instead of big T for tension because we also have period involved in these problems and it can be really confusing. So this is force of tension. For the washers, I've called this M sub W for mass of washers. Here's the free body diagram for the washers. There's tension up and then the weight of the washers down. And those are actually equal to each other because this one's not going anywhere. Now the one going in a circle actually has a net force on it because it is going in a circle. So you've got to make some predictions about what happens to the period if you increase the amount of moving mass, increase the radius, that sort of thing. And you can take a look at it and come up with some ideas of what you think might happen. Let's get some actual formulas that will allow you to predict what's going to happen. So again, the moving mass is the one that has a net force on it. So the net force is moving mass times A. It's going in a circle, so it's a specific type of A, radial acceleration. And I know radial acceleration is v squared over r, so I could plug that in. Okay, and then what is the actual force towards the center? It's the tension in this problem, so force of tension. So moving mass, v squared over r, is the tension. And when it says radial acceleration, it means this, v squared over r. Okay, good, and that's equal to the tension. But keep in mind, this is uniform circular motion, so things are going in a circle at a constant speed. The speed is the distance around, so that's the circumference of a circle, 2 pi r, divided by the amount of time it takes to go around one time. And that's the period, the amount of time it takes to go around once. So if you count the amount of time it takes to go around 20 times, you can figure out how far it's traveled if it went around 20 times, that sort of thing. So in the lab what you do is you let it go around maybe 10 times, get that total time, divide it by 10, and that would be the time for just one time around. And then you can figure out the speed that way. So there's a few questions. How fast are you going? Well, you can get the speed from this. What's the radial acceleration? Well, that's v squared over r. What's the net force? Well, that's m v squared over r. That would give you the net force. And in reality, what's providing the net force? Well, it's the tension. And I know the tension from the free body diagram here has to be equal to the weight of the hangers. So the weight of the washers here. So mass of the washers times g. Okay, so that'll help you answer a lot of the questions. I've kind of taken what I have up here and put it into one concise formula. So here's what you see: mass of the moving mass, v squared over r. But I can put in this expression for v. So v is 2 pi r divided by the period. I can take this for v and plug it in here. Okay, that's what I've done in the next step. So moving mass divided by r, that's still over here, and then v squared. So v squared would be 2 pi r divided by the period, that whole thing squared. Do a little bit of algebra, you'll see that there's an r squared here and an r there, they cancel out. So you get 4 pi squared r times the moving mass divided by the period squared. So this whole thing here reduces to this. And then you know that that's equal to the tension. And you also know that the tension is equal to the mass of the washers times g. So then you can predict what happens to the, if you increase the moving mass, what happens to the period, that sort of thing. So if you don't change anything with the hangers, if you make the moving mass bigger, what has to happen to the period? Because this isn't changing, that sort of thing. So again, you can kind of make some educated guesses, but this is really the way to to look at this if you want to, do a prediction and really know what you're talking about. You've got to base it on something. So base it on this sort of thing. Okay. Hope everything's going well. Send me an email if you have any questions. Let me know if you want to meet in a WebEx sort of FaceTime environment. We can talk about this as well. Okay. Talk to you soon.